All right, let's talk about absolute zero. We all kind of have this picture in our heads, right? It's the coldest anything can possibly get. It's the floor, the absolute bottom of the temperature scale. But what if I told you that the simple definition we all learned in school, it's not just incomplete, it's actually misleading. So today we're going to tear that old idea down and build a brand new, much more accurate understanding of what temperature and its ultimate limit really is.
But first, let's start with the familiar story. You know, the one you'd find in pretty much any high school physics textbook. It's a really simple and honestly a pretty elegant idea that goes back centuries.
So you had scientists way back when who noticed this incredibly consistent pattern. When you take a gas and you cool it down, its volume shrinks. Simple enough. And if you plot that relationship on a graph, you get this perfect, straight line. So what do you do with a line like that? Well, you just follow it. You extend it all the way down. And the point where that line finally hits zero volume? That's negative 273.15 degrees Celsius. We call it 0 Kelvin. And this gave us our nice, neat definition of absolute zero. It's the temperature where all the little jiggling and vibrating of atoms and molecules just stops. Total, complete stillness. It's a great story, right? It makes perfect intuitive sense. But the moment you start to poke at it, even with a few simple questions, the whole thing starts to feel a little shaky. Is it really that simple? Well, you probably guessed the answer is a big fat no. And this is where the cracks really start to show, because this simple model leaves us with some seriously tricky puzzles. Let's look at a few of the problems that pop up when we look a little closer at this whole temperature is just motion idea.
Okay, so just to be super clear, here's the idea we're about to put under the microscope. The textbook definition says temperature is nothing more than a measure of the average kinetic energy, the motion of particles. More jiggling means a higher temperature. Less jiggling, lower temperature. Seems straightforward.
Okay, check this out. Imagine we have a thermometer, and it's sealed inside a perfect vacuum. There are no air molecules inside, nothing to jiggle around. So, according to our definition, what should its temperature be? Absolute zero, right? I mean, no particles, no motion. But we know that's not what happens. If you put that vacuum bulb in the sun, the thermometer's reading is going to go up. So, how can a vacuum with no moving particles even have a temperature? Oh, and the puzzles don't stop there. Think about this. Why does a pot of boiling water just sit there, stubbornly at 100 degrees Celsius, even when you're cranking the stove up to full blast? You're pumping tons of energy into it, but the temperature doesn't budge. Or what about a radioactive crystal that's been cooled all the way down to absolute zero? A single atom decays, and poof, its temperature rises, even though it's completely isolated. And maybe the biggest nail in the coffin, quantum mechanics tells us that even at 0 Kelvin, particles are still moving. They literally never stop. So yeah, our model is definitely missing something huge.
So, to solve all these head scratchers, we don't actually need to throw out our thermometers. What we need to do is completely redefine the very energy they're supposed to be measuring. This is where a new framework comes in that honestly clears up all the confusion. Let's get one thing straight. The problem isn't with the concept of absolute zero. The problem is that for centuries, we've been using a super limited, incomplete definition of what thermal energy even is. We've been staring at just one piece of a much, much bigger puzzle.
So let's introduce a much more complete idea called dynamic energy. See, instead of just thinking about kinetic energy or motion, dynamic energy is actually the grand total of three different but totally interconnected parts. You've got potential energy, which is stored in chemical bonds and in the orbitals of electrons. Then you've got kinetic energy, the motion we all know about. And finally, you have radiative energy, which is carried by things like light and heat waves. Now, here's the really cool part. These three forms of energy, they aren't separate. They're not just sitting in their own little buckets. They are constantly changing, morphing from one type into another, in what we can think of as a kind of energy triangle. And this image right here illustrates that relationship perfectly. You can think of it like a closed loop. Radiative energy gets absorbed by an atom and is stored as potential energy. That potential energy can then be released, creating kinetic energy, actual motion. And then that kinetic energy can get converted back into potential and radiative forms. It's this constant dynamic dance. Let's quickly break down how that dance works. An atom can absorb radiation, right? That energy gets stored as potential energy when one of its electrons jumps to a higher orbit. Later, that electron can fall back down, releasing that potential energy as radiation again. But the key piece, the one that connects to motion, is a process called transimpact. Just think of it like this. When that stored potential energy suddenly changes, it creates a tiny physical pop that literally pushes on nearby atoms, and boom, you've got kinetic energy.
The reverse of that, impact trans, is basically just friction, where collisions turn that motion back into other forms of energy.
This visual here shows that exact trans-impact moment. An electron soaks up some energy and jumps to a higher orbital. When that happens, the atom's electron cloud physically expands, like a tiny balloon inflating, and it shoves its neighbors away. It's like a microscopic explosion that kicks off all those particle vibrations we call heat. So you see, kinetic energy doesn't just appear out of nowhere. It's born from changes in potential energy.
Okay, so now that we have this much better model of dynamic energy, let's go back to those puzzles from the beginning and see how they suddenly start to make perfect sense. Remember the boiling water? Why does the temperature get stuck at 100 degrees? Well, as this quote explains, during a phase change like boiling, the temperature we measure with a thermometer basically gets decoupled from the kinetic energy. All that extra heat you're adding isn't raising the potential or radiative energy anymore. Those have maxed out for liquid water. Instead, all that energy is being funneled directly into kinetic energy to kick the molecules out of steam. Since the parts the thermometer can see aren't increasing, the reading stays flat, even while the hidden kinetic energy is going through the roof. But honestly, the biggest failure of the old kinetic energy-only model is how badly it predicts something called specific heat, basically how much energy it takes to heat something up. For a simple gas with single atoms, the old theory works just fine. But look at a complex molecule like octane. The theory predicts a number that is off by a factor of more than 14. That's not a small error. That is a massive, catastrophic failure of the model that physicists have known about for ages.
And this graph, this is the solution. It is the smoking gun. When you stop looking at just kinetic energy and instead plot specific heat against the number of chemical bonds in a molecule, which is a measure of its capacity to store potential energy, you get this. A nearly perfect straight line. The correlation here is 0.98. In science, that is about as close to a perfect match as you can possibly get. This is the data telling us loud and clear that the energy needed to raise a temperature is overwhelmingly about storing potential energy in bonds, not just making molecules move faster.
So, with all the puzzles solved and the data making perfect sense, we can finally put together a new, much more complete picture of what temperature and absolute zero actually are.
Here is the single most important takeaway. Temperature is not just a measure of particle motion. It is a reflection of the total overall level of a system's dynamic energy that combines some of its potential, kinetic, and radiative energies. Motion is just one part of a much bigger story. And that leads us to our new correct definition. Absolute zero is not just when kinetic motion stops. It is the state where all three components of dynamic energy hit their absolute minimum possible level all at the same time. To get to true absolute zero, you have to eliminate all radiation, stop all particle vibration, and make sure every electron is in its lowest possible orbital. All three have to be at rock bottom, together.
It's a huge shift in how we think about something so fundamental, and it really leaves us with one last big question. I mean, we thought we had temperature completely figured out for centuries. If our understanding of something that basic was this wrong for so long, what other foundational concepts in science are we just taking for granted, waiting for someone to come along with a new perspective that reveals a much deeper truth?